So, hello everyone. I hope you can hear me well. Thank you for coming and thanks for showing interest in my today's presentation. Today, I will give you an outlook about a comparison of three refrigerants in food retail applications, namely R-454C, R-449A, and R-744. There has been developed a steady state model based on MATLAB, with a focus on energy efficiency and system performance. Before I start, I would quickly like to introduce myself to all of you. My name is Dominik Düing. I'm working for Chemours, Germany, and I'm supporting customers for implementing new low GWP HFO refrigerants. So let's get started. I think we're already on time. So small introduction up front into the topic. So why does the system efficiency matters, especially in food retail applications? And there are a few reasons you're going to show up here. So roughly 8% of the global electricity consumption is used for food and refrigeration. About 40% of all food globally requires refrigeration. And the numbers are increasing over the years. And up to 60% of the energy which is used in small to mid-size supermarket stores is related to refrigeration. Just to give you a little outlook, when I'm talking about small to medium-size supermarket stores, I'm talking about sales areas for up to, let's say, 1,500, 2,000 meters square. The overall system emissions account for direct and indirect emissions, and about 95% out of the 100 are related to indirect emissions. All those reasons lead to the follow-up that the energy efficiency of the refrigeration system is one of the key elements in order to reduce the energy consumption. So we need very high efficient systems, as well as reducing the carbon emissions of the system. Considering the supermarket energy usage, we identified four main pillars, which are a big part of the overall emissions and the overall energy usage. Obviously, the size of the supermarket directly transferred into the energy usage. Then we have also the merchandising strategy, which also means there are different parts of medium temperature used and low temperature refrigeration is used. And the location, of course. So do we talk about in a hot climate or a climate where it's like barely low temperatures over the whole year? And last but not least, the equipment, of course. So the system is a very important pillar, and the systems are using refrigerants are regulated starting here, for example, the 1987 with the Montreal Protocol, followed by several other regulations. Just this year in April, I think it was 11th April, the latest F-gas regulation. So all those regulations are there to force the phase down of high GWP refrigerants. Refrigerants like 404, 547A are being replaced by substitutes by lower GWP alternative solutions. And they've been developed over the past years, and more systems come into the game to different sectors. Some of them are named here. So like 454C, we have also 449A, which is probably one of the most used refrigerants in food retail applications, and also R-744, which I would say took up in the last 10 to 15 years more and more. Very important, the choice of the refrigerant impacts not only the architecture of the system, but as well the energy efficiency, also the durability. Let's look a little bit further into the scope of the study. I already mentioned it. The presentation is based on a study done by the Politecnico di Milano in Italy. The aim or the key was of this study to determine the optimal refrigerant choice in order to increase the energy efficiency, decrease the energy usage, of course, and also lowering the overall emissions. Considerably was here the supermarket layout. So they have used an existing store layout from a supermarket, and based on this, they have developed this model. They've used 3 fluids or 3 refrigerants, which were compared in this study. Again, it's 454C, 449A, and R-744, based on 2 locations representing a hot and a mild climate in Europe, namely Milano and Palermo in that case. Let's look a little bit further into the details. So I already mentioned, so this is the existing store layout which has been used. It is a steady state model based on MATLAB. And on the lower left part, we see the cooling loads as well as the evaporating temperatures. So we have the medium temperature 1, where we evaporate at -2 degrees Celsius, where we have roughly 32 kilowatt cooling capacity. Then we have the medium temperature 2, where we evaporate at -10, 33.5 kilowatt. And the low temperature load is about 27.4 kilowatt. We're evaporating at -35. Based on all of those assumptions, the 2 systems have been used to compare the fluids with each other. The upper right side, we see a very, very simplified, one of the easiest technology systems based on HFC, HFO. So 449 and 454C were based the results on this system architecture, while they've used for R-744 a more advanced architecture, I would say. So we have for example, we have a power leak compressor, we have a flash gas bypass system, as well as an internal heat exchanger, so liquid line, suction line heat exchanger. Like to look a little bit more into the fluids itself. So first 2 rows we see 454C and 449A, and both fluids are pretty much comparable. The thermodynamic properties are similar, and the handling itself, except of the flammability, the mild flammability of 454C, they're pretty much pretty similar to each other. While CO2, we see they have a much higher pressure, and therefore the impact of this we're going to see in the next slides. A pretty important point, what I would like to mention at that point is the recoverable. So especially considering F-gas regulation and also the overall part of the circular economy, it's key for us and for the whole value chain to not just use the refrigerant and also to reuse them. So recycling, recovering, to get the refrigerants back and keep them in the value chain as long as possible. Looking at the results, on the left-hand side, you see a graph where we see on the y-axis the cooling COP of each system, and on the x-axis we see the air temperature. What we can conclude here is that below 15 degrees Celsius ambient, based on the thermodynamic properties of CO2, we see higher efficiency here. But above that, the HFC, HFO alternatives are way above the efficiency of the CO2 system, especially considering the big drop at 20 degrees Celsius based on the transcritical operational mode. So let's look into energy savings, and left side again, I mentioned it. So it's 2 climate zones kind of. So we have Palermo and Milano in that case. The results for Milano we see on the left-hand side. So what we see here is in the mild climate that the HFC HFO solution in that case, 449A, that we have a higher efficiency of up to 10.9%. And considering hot climate, we're up to 13.6% higher in efficiency. 2 slides back, I was talking a little bit about the architectures of both systems based on the thermodynamics of each refrigerant. And we saw that the CO2 system is way more advanced compared to the HFC HFO based system. Another part of the study was to include a small layer of complexity in order to see the impact of an internal heat exchanger. And very important here, without changing the regulation on the system, kind of just adding one layer of complexity, one part, the internal heat exchanger, and seeing the impact of the efficiency in that systems. What we see now is that the efficiency has gained by roughly up to 4% by just adding an internal heat exchanger. And if we consider those results to see how do we translate this into cost savings as well as lowering the overall emissions, the 17.4% of higher seasonal COP will lead into roughly €18,600 yearly energy bill savings for a single supermarket. While looking to the emissions, the other hand, if, for example, all supermarkets in Italy would use one of the HFC HFO-based solutions, the yearly savings would lead to another 4,000 electrical cars, each traveling 1,000 kilometers. So that was a quick outlook. These are the conclusions. What we saw, or what the study showed, is that below 15 degrees Celsius ambient, that COP showed or had an advantage in the in efficiency performance. Above that, we saw that 449N as well as 454C outperformed CO2 systems based on, again, very simplified system and also adding one layer of complexity using the internal heat exchanger. Takeaways. What is very important, I mentioned it at the very beginning. The study was based on an existing supermarket store layout for small and mid-size, up to, let's say, roughly 2,000 meters square of sales area, that we have to consider and evaluate for each application, what is my right refrigerant. 454C and 449A enable and can outperform CO2 systems, way more complex CO2 systems, while maintaining very simple layouts, robustness, and ease of maintenance. I was just mentioning, by just adding one layer of complexity, we gained roughly 4%, adding an internal heat exchanger. There was an evaluation ongoing from an institute in Germany. They looked into high-efficient 454C systems, and we've used that to calculate further on the code and so on the refrigeration side. And what we see is, yes, we have an impact in internal heat exchanger, set at roughly 4%. But if we keep improving the system, while especially looking into the system control, superheat control, adjusting that based on the refrigerant, based on the system, we can achieve very, very high cost savings. So COP improvements for up to 36%. And very important, 454C is an A2L refrigerant. And in some areas, we are limited based on the EN 378 with charge limitations. And this is another key enabler to improve the cooling capacity of such system. So we can have small systems, same charge or low charge systems, and increasing the cooling capacity by up to roughly 40%. So if you're interested in having a deeper discussion on that, we are in Hall 7, stand 250. Please join us. You're welcome to come around, and I'm happy to discuss this with you in more details. Thank you very much, and that's all from my side.